in engineering, we start from the simple, and then we complicate it, as it were, to meet with reality. Okay, sometimes the simple form that we start with might not even be realistic, but it teaches us something. So, like in thermodynamics, you want to represent the behavior of a gas, you start from ideal gas. Then, as you develop along virial equation and equations of state, and then it becomes complicated. You end up with something that represents a reality. In mass transfer, the same principle is applied. When we started out, we were looking at molecular diffusion. So I told you that you can imagine that we are in a room where all the doors and windows are closed, fans are shut off, and then you release some gas in one corner. Then it finds its way into all corners of the room, and it just happens by molecular diffusion. So in that kind of situation, there's no bulk movement of the gas because the windows are closed and everything. In industry, you can't always do that. Even at home, you don't do that. When you prepare your tea or your coffee or your whatever, you push sugar in there. You don't sit down and let the sugar dissolve to all corners of before you drink it. You don't have time for that. No more do they have time to wait in industry. So you move things around, you pump things around, you use compressor, you use blowers and all of those kind of things in order to hasten the process. But whilst you are allowed to do that in practice, once you do that, then this is your equation that we keep bringing up. Is it the CA?
Yeah.
Plus NAX forget it. You can't solve it. Okay? If you could solve it, then we wouldn't have any problem. We wouldn't be doing any of the things that we are going to be doing subsequent to it. We can't. Because we can't solve it, we are forced to do something about it. And what we do is we define, that's where the concept of mass transfer coefficient, heat transfer coefficient, that's where they come in. You define an equation, Na is equal to Kc delta C. So the flux is equal to the driving force, which is the delta C. And as I said, 1 over Kc by resistance, and that is it. And all you want to do then is to find Kc. If you can get Kc, then the problem is done, because normally the delta Ca can be obtained from the subscribing the problem. So in convective mass transfer, when you express this equation in okay. Okay, if we replace, let's say Na, I actually give Na bar as C the AB grad X bar A plus CA. Okay. So if you substitute for, now if you write Na as such, then in vectorial form, Na is a vector that consists of Nax, Nay, Naz. So you can use the vectorial form which is, I can pull it out of here, is del CA over del T plus a bar is equal to RA. So if you plug this in that, well, this is that. If you plug this in that, then you are going to have a very complicated looking equation. Del CA del T minus got C the AB x bar A plus grad dot CA is equal to RA. Now, this equation looks easier, is more easy to grasp. But this is the same equation as this, except that we have replaced the NAs with this expression. Okay, we are substituted for NA. Okay, in fact, this equation probably should have come here, because when you expand this, this is what you get. You expand this, this is what you get. And then we have substituted for the NA, which is this, and then you get this. If you recall, in lecture 2, we derived this equation, and then we set up all kinds of conditions to simplify it. For instance, we said, suppose C is constant, or suppose the density is constant, it's the same as. And then suppose the diffusivity is constant. It means all of this get pulled out, okay? So if your situation is steady state, once again, this one goes, and suppose the concentration or density is constant, and you have C, the AB, all coming out, then you have this thing, XA, okay? Then plus you have this. This one, if you go back, you find that we expanded it. We expanded it and applied the fact that composition is constant or density is constant. If you expand it, it's like the differentiation of two terms. You hold one, you bring, and so on. So if you do that, then one of the terms will drop out. Then you are left with this CA. It will be V dot CA. And if the reaction is constant, this one also drops out. RA, the reaction is constant, this one also drops out. Okay, and then you are left with this. But to get here, we've had to make all kinds of adjustments before we get here. So it is never possible to solve this equation or this with all the necessary terms and conditions that can go with it. So to simplify that kind of situation, we define, this is the defined equation for mass transfer coefficient, and we go about trying to find what Kc is. What is this mass transfer coefficient for the phase that we are dealing with? Okay, and mind you in convective transfer, you have a surface, and then you have, let's say, gas. So material is going from here to this phase, okay? And you are trying to find the rate of, or the flux for the material going from, let's say, A, going into this, and so on. And you do it by determining the mass transfer at the surface. If you determine the mass transfer at the surface, then you have an expression for Na, out of which you can extract your mass transfer coefficient, Kc. If you have a way of determining the mass transfer going from the surface into the bulk of this, then you get an expression and you compare that expression to the defining equation for mass transfer. And it will allow you to extract the mass transfer coefficient Kc. You understand? So we have made this definition for mass transfer coefficient Kc. And we want to find what Kc is. If by some means you get another expression for Na, then because that expression will involve delta Ca, you can get your Kc out. So, okay. Now, the Kc is a function of, it's a complicated kind of solution. It's a function of the properties of the fluid. Example, its density, its viscosity, its concentration. All those, they play a role in determining the mass transfer coefficient. It's a function of the dynamic characteristics of the flowing fluid. Okay? How fast is flowing? I don't even state it. But the velocity at which it's flowing, is the flow laminar, is the flow turbulent, and so on. So they are all part. And also the geometry of the specific system of interest. Is it flow in tubes? Is it flow over a flat plate? Is it flow over a bundle of tubes or pipes or whatever? Particularly heat transfer, that can be very important. So by listing there are various methods of determining the heat transfer coefficient. When you have complicated functional dependency like this, one of the methods that you use is dimensional analysis. I don't know if you did dimensional analysis. Fluid flow. You did dimensional analysis in fluid flow, fluid mechanics. That's where everybody does it. I mean, because once you do it there, then you can use it in mass transfer, you can use it in heat transfer. So you don't do it at this point. When at the time you were doing momentum transfer, fluid flow, you should have done dimensional analysis. That's fine. But so at this point, I'm just assuming that you know how to do that. Okay, you know dimensional analysis. Maybe in future, along the line, if you need to know it, if you didn't do it, and you need to know it, then you have to go back and study it. Now, so that's one method of determining the Kc. You write Kc as a function of a whole bunch of properties, then you group them up, then you do your... then when you do that, you also need experiment to the way it's done. You do that theoretical analysis. No, you use the experimental data to also complement your analysis. So apart from dimension analysis, you can do exact boundary layer analysis. Now, exact boundary layer analysis means what? Exact boundary layer analysis means that you have to solve the equations. These equations, depending on which ones that you can get solution to. You have to solve it so that you use it to define a flux equation, or use it to get an expression for flux, and then you go back to the defining, and then you extract your heat transfer coefficient. The thing about the heat transfer, the mass transfer coefficient, is that once you get the mass transfer coefficient, or once you have a correlation for mass transfer coefficient, if you want to know your flux, all you have to do is use that equation. That's it. Or use whatever correlation that you be given to get the heat transfer, mass transfer coefficient, and then you use the defining equation, and then you got your flux. Okay. Okay, so the method that we use exact boundary layer analysis. We'll see about that, and then you can also use approximate boundary layer analysis. Okay. Approximate means that you have skipped solving these equations in its analytical complete form, and another method that's also used is the analogy between momentum, heat, and mass transfer. That's also that we'll see about that maybe next week. Okay. So dimension analysis will leave out let's see exact boundary layer analysis. But before we do that, in any of these methods, whether dimension analysis, exact boundary, or approximate, you express mass transfer correlations, mass transfer coefficient correlations, as well as heat transfer coefficient correlations, all kinds of correlations in momentum transfer as well. You express them in terms of dimensionless parameters, okay? So transfer phenomena correlations are normally expressed in terms of dimensionless purposes, for purposes of parameters, for purposes of generalization. But once you do that, then you don't need any specific units, because the parameters are dimensionless. Because they are dimensionless, means I can use any units for them. So first of all, the molecular divisibilities of the three transfer phenomena are defined as such. This defines the momentum divisibility nu or kinematic viscosity. Okay. Mu, no. What is this? This I've forgotten this one. What's the Greek name for this? Mu. Okay. Mu over rho is the dynamic viscosity. So nu is the kinematic viscosity. Okay? And then you define thermal divisibility alpha, which involves the thermal conductivity, the density, and the heat capacity. They all have the same units. Okay? These three divisibilities. Mass divisivity, is meter square per second, centimeter square per second, and so on and so forth. Now, so the ratios of these divisibilities define dimensionless parameters which are relevant in mass transfer studies. Because they all have the same units, if you divide one by the other, you end up with a dimensionless number. So we define Schmidt number as the momentum diffusivity, which is nu over mass diffusivity. It is dAB. So remember that nu is equal to mu over rho. So this gives you what you call the Schmidt number. The analogous number in heat transfer is the Prandtl number. Okay. So Roger, take note. This should be PR. It's not Schmidt number. It's Prandtl number. Prandtl number. Where K in this case is the thermal conductivity of the fluid. K is the thermal conductivity. And then we also define Lewis number. The Lewis number is the ratio of thermal diffusivity over mass diffusivity. Okay. Lewis number is relevant when the process involves the simultaneous convective transfer of mass and energy. For example, in drying. Okay, it's not only drying, humidification, drying, crystallization, all those processes involve simultaneous transfer of heat and mass. And then there's Sherwood number. Sherwood number is convective mass transfer coefficient over molecular mass transfer diffusivity. So that's defined KCl over dAB. And the heat transfer analog in for Sherwood number is the Nusselt number, which is so defined, where H is the heat transfer coefficient and K is the thermal conductivity. These dimensionless groups are used in dimensional analysis. Okay, so now we have three situations that we look at. We look at exact boundary layer analysis, approximate boundary layer analysis, and then, but not today, next time we will look at the analogies between the momentum and so on. Then we'll do interface mass transfer. That'll be next time, then we'll finish. Okay, so if the concentration profile for a given flow, for a fluid flowing over a given surface is known, then the mass transfer coefficient can be determined by applying the defining equation. I told you the defining equation, Na, for instance, is equal to Kc times delta C, and therefore the concentration profile, the concentration occurs in it, okay? So we have Na equals Kc delta C. Delta C is nothing but the concentration profile. The profile can, in theory, be obtained by solving the general differential mass balance, the general differential mass balance equation. Yeah. Now, an analytical solution of these equations has, however, been obtained for only the simplest of cases, namely flow under laminar conditions, not turbulent conditions, over a flat plate, not a tube. The steady state, not unsteady state. So all of those things. So the general steady state balance with constant composition or constant density, no chemical reaction, is given by equation 14 of lecture 2. And that is this equation. This equation I showed you. This is for steady state. This is for no chemical reaction, constant composition. One of the terms here drop out. So if you go back to lecture 2, equation 40, you can see how you end up with this equation. Now, as I told you, this equation is nothing but this equation in fluxes, and we have replaced the fluxes with these expressions because they contain concentration, okay, and they also contain velocities. This V is nothing but a velocity vector, okay. So we are dealing with a situation where the fluid. Now, first we started by shutting the windows and exhausts. Now we've opened them. The fluid is moving, okay? So the velocity of the fluid needs to be taken into account in solving. And this is where it appears, okay? Okay, if you expand this equation, then you end up with this. Because, mind you, these signs, they are all like shorthand for derivatives. So if you expand them, then you end up with this, okay? Now, this is for three-dimensional flow. You have variation x, y, z, x, y, z. But we are looking at flow over plate, okay? So the plate is like this. And flow is going like this. We are calling this the x direction. And if the z would be here. This would be z. And then the flow, this would be y direction. Okay? But we are not interested in the variation in the z direction. Okay? We are interested in two-dimensional flow. We are interested in the flow in the x direction because this is where the fluid is moving. The fluid is moving in the x direction. But there's going to be variation of velocity and concentration in the y direction. You understand? The concept of boundary layer was first introduced by Prandtl. He was a German. I don't know whether he was an engineer, but he was German. And the idea of the boundary layer was that he said the resistance to flow is confined if you have fluid flowing in a tube or across the surface, the resistance to flow is confined to a small thin layer on the surface of the flow. And that as you move away from the surface of the material, the resistance diminishes. And the region within which this distance is felt is what he described as the boundary layer. So, for instance, if you have a plate and you have fluid moving across this plate, what it means is that the liquid that touches the very surface of the plate is going to be trapped on the surface. It's like rolling a carpet. The first layer of fluid that touches the surface is going to be caught on the surface. And so we have what you call the no-slip condition. That the fluid does not drag itself across the surface, but the first layer just stays there, and then the next batch, roll along over that initial surface. So what that means is that if you are looking at the variation of velocity, this is your y direction, and this is your x direction. If you are looking at the variation of velocity in the y direction, here on the very surface of the material, what would the concentration, what would the velocity be? The velocity will be 0. But as you move away from the surface, then you have some velocity. So normally, you find it in books, they would draw something like this. So the velocity is 0, but then as you move, you reach some surface, then the velocity will become the same as what. Now, this situation, if it happens here, it would the maximum velocity will probably occur at this point, and if it happens here, then and so you end up, you can draw a line like this. Okay. Beyond this, within this area, you have the full velocity, which we designate as v, like that. Okay, that's on the outside of this space. Define what we call the boundary layer. Okay, it is a very small thin surface, at least that's how we picture it. But we have in a drawing like this, you have exaggerated it. Okay. But certainly you can imagine that something like that will happen, because if you have a pipe and you have a flow within the pipe, the liquid does not come out like this, like toothpaste. It comes out looking like this. Okay, so the profile, the velocity profile in the case of a tube is a parabola, and you can derive it. And experiment have shown that's how it happens. Okay, and so there is variation of velocity because of the nature of this. There is variation of velocity v at a given point x. So that is x. If you write vx, it means the velocity at a given point like this. So that itself is going to vary. Now, this velocity at a given point is going to be a function of y, right? So if you are standing at this point x, the velocity x at a point is going to vary with y. So the velocity at x is a function of y, right? Okay. Now, the velocity, of course, would also of x would also be a function of x, right? That's not hard because you are going. So the velocity at each x will be a function of where you are. Okay. So okay. So this equation is what we are looking at. We are interested in determining the concentration profile of material which is flowing on a flat plate. So the plate has a certain width, and then it has a certain length. But we are interested in the variation of concentration in the direction of movement of the fluid, and also in the direction perpendicular to it. Okay. Previously, there was no flow. We were looking at molecular, but now there is flow, and therefore these equations, Vx, Vy, and so on, are not constant, or they are not zero. Okay. Now, we are looking at two-dimensional flow. So if you are looking at two-dimensional flow, then we can drop one of these terms. We are looking at variation in the x direction, and in the y direction. We can drop the flow going inside. The flow going inside will be the z direction, but we assume that there's no variation there. Okay, so that one, it doesn't interest us. So we can drop this one, and then we are left with these two. Okay, and then on this side, the same three-dimensional, but we are looking at two-dimensional. So we drop one. Okay, we drop this term. Now, the two-dimensional terms, once again, in order to get a solution, strictly speaking, like we should take all of that. But we make the assumption that this term is small. Okay? We make the assumption that the square CA, the XY, is small in magnitude compared with the variation in Y direction. Okay. The square CA, the XA, we know that the velocity or the concentration, whichever, going in this direction is going to vary because there's going to be transfer of material from here, adding to the fluid. And so definitely by the time the fluid reaches here, it has the concentration has increased. And so it will have the CA will not be equal to 0. It is like drawing a curve. You draw this. It has a slope. Okay, so the y, if you like, the x, the y dx is not equal to 0. Okay, but if you had a curve that looks like this, you had a curve that looks like this, then you can see that the dy dx is going to be varying. So the slope itself is going to be varying, right? So for this curve, you can say the square y, the x squared It's not equal to 0 for the second curve. But for this one, the square y, the x squared will be equal to 0. But the original slope is not equal to 0. It's the variation of the slope. That's what this term represents. So in other words, we are assuming that we have a curve that varies in slope. But the slope is so small, if you like. So the variation, the rate of variation in the x direction, we assume that is small. Okay. And that way, we are able to drop this term. Okay, so if when we drop it, we need an expression for Vx, Vy, because these terms, as I explained to you, they vary as along the x-axis. They are not constant. So, what is the relationship between Vx and Vy and distance? That relationship is obtained from differential mass balance equation. It's called a continuity equation. It has been simplified, and for a two-dimensional constant composition fluid, this is what you end up with. Okay, if it's two-dimensional, the composition is constant or the density is constant. Okay, so in trying to solve equation 3, you have to add equation 4 to it, and then you solve the two simultaneously. Okay, because equation 4 accounts for the variation of Vx and Vy, okay, which are not constant. Okay, they are different functions. So it's a simultaneous, if you like, differential equation, partial differential equation that you need to solve. Okay. So the solution of 3 and 4 will give you the concentration profile. Equation 3 can be compared. Well, so now we have established that these are the equations that we need to solve. But what we do is, and that is why you always start with the study of fluid mechanics, fluid flow. In fluid flow, somebody has solved this thing long ago, Blasius. So he solved this equation. This equation comes in fluid flow from the Navier-Stokes equation. When you do your force balance to arrive at the Navier-Stokes equation, then you get this, okay? And then you do your mass balance, you get the continuity equation. In fluid flow, once again, then you get this. So somebody has solved this two together, okay? And what we want to do is to solve this, and this. So the two, if you look at the two, instead of Vx, we have C. But instead of nu, we have DAB. Okay? So in the analogous equation in heat transfer is this, where the four been solved using the original solution by a fellow known as Blasius, the previous solution. Okay, so the mass and heat transfer equations, that's equation 3 and 6 respectively, are solved by comparison to the solution of the fluid flow equivalent, namely equation 5. And in each case, employing equation 4. Okay? So equation 5 is what has been solved, but to get Vx and Vy, because they vary, you use this. So the two together. The same way, you solve equation 3 and this, or you solve equation 6 for heat transfer with this. Okay? Now, These equations are solved by first, you dimensionalize the variables. For the momentum transfer, these are the dimensional variables that are used. Vx, Vxs on the surface, and V nu. V nu, as I told you, is the velocity on the edge of the boundary layer. The Vs is the surface. Obviously, when it comes to concentration, the velocity Vx on the surface is what? Vx on the surface will be what? Will be 0. So at y equal to 0, y equal to 0, y is going to this direction. So y equal to 0 is at the surface. Okay? So if Vx, that is the velocity at the surface, that is 0, or the velocity at the surface is equal to Vx is equal to Vs. That's also one way of looking at it. The velocity at the surface, velocity at x, at the point x, y is equal to 0 means at the surface. Okay. So Vx at y is equal to 0 is equal to Vxs. You understand? So that gives you the 0. Okay. Because this becomes Vxs. Okay. Now, the velocity at y infinity, Vx infinity, will be the same as the denominator. And that gives you 1. So the concentration also can be expressed in the same form. Look at another error. So let's change it. Take note. It should be equation H. Okay. Now, if you compare the two equations, the one for fluid flow, this one, equation 5, and the one for mass transfer, equation 3, the two solutions will be identical provided the diffusivity dAB is equal to nu. Okay? So comparing equation 5 and 6, the two are identical when nu over 5 is equal to, which is equal to the Prandtl's number, is equal to 1. Okay? That is the flow, and then I think that's the heat transfer. The flow and the heat transfer. Now the flow and the mass transfer gives you nu over d, which is the Schmidt number, that's equal to 1. Okay, so the two terms, the two quantities are identical. Is equal to this for heat transfer. If this nu is equal to this, then that is the situation where the Prandtl's number is equal to 1. And then for mass transfer, if this is equal to this, okay, then the two solutions should be identical. And in that situation, we have the Schmidt number is equal to 1. So for heat transfer, the Prandtl's number is equal to 1, Schmidt number is equal to 1. Then we can just use the Blasius solution for momentum transfer or fluid flow. And that is given like this. If you want to know the details about how you arrive at this, then you have to go back to the original paper. But this is a solution found in all kinds of textbooks. Nobody bothers to go back. Okay. So here we are. For momentum transfer or fluid flow, he got this, and it's equal to 1.328. We write a parallel equation for for mass transfer equal to 128. So from this solution, then, we need to get our concentration gradient by differentiation. Now he defines an F dot. You know, if you go back, you see that he has the F dot over psi or zeta, and then this function. And these are the expressions for those F dot, and then from this, is it eta? Okay. But we are just interested in this one, okay? This is what we get when we differentiate, we do this differentiation. So it is 2 here, see 1 over 2 here. If you go up, then it will come 1.328 over 4, and that will give you your 0.332, okay? But this differentiation, this is a constant, CA not, these ones are constant. It's only CA that you are going to differentiate. And here is only Y that you are going to differentiate, okay? So if you do that differentiation, then you get the CA dy at Y equals 0 is equal to this expression. So that directly comes from here. And I'm just showing you how the 0.33 comes, because this 2 comes up, it flips up, because it's 1 over, it flips up. Then this is 1.32 divided by 4. Okay, so it's like approximately 12 divided by 1.2 to be 4.3 something. Okay, so that's what you get. Now it says, since the Blasio solution for momentum case did not involve a velocity in the y direction at the surface, the concentration profile also involves the important assumption that the rate at which mass enters or leaves the boundary layer at the surface is so small as not to alter the velocity profile provided by the solution. Well, this is a mouthful, but this is what it means. Okay, if the fluid is flowing alone, just the fluid, there's no mass transfer, it's going to develop a boundary layer. And in fluid flow, the boundary layer is called this, del, without any. Now, if the fluid is flowing and there is either heat transfer or mass transfer, that is also going to have its own boundary layer. Okay, so the concentration is going to, the fluid is flowing, the concentration is going to be something Ca at the surface, and because material concentration is high and is going to reduce until it gets to some point, then the concentration also will flatten out. Like I'm trying to get an equivalent. For velocity, it's clear. The velocity is 0, and then it increases up to some point, and then the bulk. But for concentration, it's the reverse. It is high at the surface, but as you go away from it, it reduces. Okay. Now, that variation in concentration would also be confined to some boundary layer. For the rest, the bulk of it is going to mix up. Then the concentration is the same. But within a certain space, which constitutes the boundary layer for concentration. So what it means is that this boundary layer for velocity doesn't necessarily correspond to the boundary layer for concentration or the boundary layer for heat transfer. Okay. The boundary layer for concentration, normally we call it del, and then we abbreviate it C. In other words, for some surface on the for a little distance from the surface of the plate up to some point, there's going to be variation in concentration, but in the bulk, it is the same, and that edge is is that length is divided by this. Now, what this thing is saying is that here there was no mass transfer, there was no variation of concentration going in X direction, no, because nothing was diffusing into it. But what we are saying, what he's saying is that here, although there's material diffusing from the surface into this, still we say that the boundary layer does not vary. Because if the material has changed, then the boundary layer could vary. But we're saying that the rate of diffusion is so small that it doesn't affect the boundary layer that is accepted that is developed as a result of the free flow. Okay. So the rate at which mass enters the boundary layer at the surface is so small. You can just imagine that if the rate is significant enough to affect the viscosity, if the viscosity is affected, then the flow characteristic is going to change. But we say that the material going in is so small that the boundary layer, the thickness of the boundary layer for the velocity profile is not affected. Okay. Okay, now the mass transfer from the flat surface into the laminar boundary layer is given by this expression. Okay? Now this is important because generally you would write that the mass transfer NA is equal to minus the AB is CA, the X or the Z plus XA, the Z, times NA plus NB, and so on. But at the surface of the plate, we are looking at mass transfer for the plate, a solid 2. At the surface, this one is 0. Okay? This one is 0. Because you are looking at transfer of material from the solid surface to the fluid just adjacent to it. There's no fluid flow component to that. It's only diffusion from solid. There's no flow which is pushing it in the solid to bring it to the surface. So this term is equal to 0. So you are left with just this one. And that would define, and therefore if you differentiate, if you plug in, you already differentiated. If you plug in this expression into equation 11, then this is what you get. Okay? And this negative has been removed just to turn these two around. Okay? So if you compare equation 12 to the defining equation for mass transfer, which is this, the original equation that we started with, Kc delta x. If you compare the two, if you compare this to this, then you can extract your mass transfer coefficient. So this is an expression for mass transfer. You see that in terms of dimensionless numbers, you just put it into dimensionless form. This is it. So what does it mean? So it means that if you needed to determine the flux from a plate to an adjacent fluid which is blowing over it, and the Schmidt number is 1, all you need to do is you need to know the X, the AB, blah, 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 Reynolds number at the point X, and then the point is, all you need to know is Kc. Once you get the mass transfer coefficient Kc, you can do that. Although we do some more work on this. So this is applicable to Schmidt number of unity. This equation is applicable to low mass transfer rates between a flat plate and a boundary layer. That one was if you recall, that one was mentioned. It's only when the mass transfer rate is low that the comparison or the equivalence between the boundary layer for a fluid flow and the boundary layer for concentration profile can be equated. Okay. Now, Polhausen has considered the solution of the same problem as above in heat transfer. So Polhausen looked at heat transfer. In the situation where the Prandtl's number is other than unity. So in that case, we look at Schmidt number equal to unity. But in heat transfer, the applicable thing, the same thing can be done for Prandtl's number of unity. But we are looking, Polhausen looked for heat transfer where the Prandtl's number was other than unity. Okay? And the Polhausen solution for heat transfer is applied to mass transfer. So he found approximate relationship between the thermal and hydrodynamic boundary layer. So the hydrodynamic boundary layer is the boundary layer for flow solely. And the relationship between the thickness of the boundary layer for hydrodynamics and for heat transfer is given as this, Prandtl 1/3. This same relationship is considered to be valid for the concentration boundary layer. So for the hydrodynamic boundary layer and the concentration boundary layer, we say that the ratio of the two is equal to Schmidt number 1/3, raised to 1/3. So what he did then was to multiply the Blasius solution, eta, by Schmidt number of 1/3. And this allowed the extension of the solution to Schmidt numbers other than unity. Okay, so you do that, and then he makes a plot of eta. You know, eta before was y over x RE. Then he multiplied by Schmidt number 1/3, and then Vys over Vs equal to 0. It means that he's looking at the surface. And then if you make a plot against the unaccomplished change, this is what it looks like. But we are interested in the slope at the point where Vy is equal to 0, and that slope is equal to 0.332. Okay. So at y is equal to 0, the concentration profile is equal to 0.332, and here he has multiplied the Reynolds number by the Schmidt number. So the Reynolds, when the Schmidt number was equal to 1, this was not there. And so this can be combined with equation 12, okay, which is the defining equation for mass transfer, to give this. So the mean mass transfer coefficient for a plate or width W and L. Because what we've done is we've found mass transfer coefficient for particular x, okay? Now, the plate looks like this. It's L from here to here, and then W from here to here. So W is the width and L is the length. Now, the expression that we have are for various values of x. And so the mean mass transfer coefficient of a plate of width W and length L is obtained by integration. You have to integrate over the entire length of the plate. Now, in this problem, this derivation, we said that the width is equal to 1. It's unity. Okay. So the total mass transfer for this plate of area AWA. Now, mass transfer rate of mass transfer is given by the flux times the area. Okay. So you see that here we have multiplied by A. Okay, where A is the area. which will be W times L, okay? But we know that the mass transfer coefficient was obtained for unit area, unit width, okay? So we have to, in general, multiply the flux by the area A. And we do that. This expression is for a specific x. So we have to, if you do the integration, then what it means is that at any value x, you are finding this or the A, this or the A, and so as x varies, you integrate over. Now, we substitute our expression for Kc in here, and this is it. Then you will find that we are only integrating from 0 to L, because as I said, we already fixed that W is equal to 1. Otherwise, this will be a double integration, but we are not doing that. Okay. So if you do that integration, then you come up with a mean mass transfer coefficient expression, which is this, which we have converted into dimensionless form, which is the Sherwood number for L. Thus, the local Sherwood number at the point X is related to the mean Sherwood number. If you look at the previous one, it was 0.332 and 0.66. And so the mean Sherwood number is equal to twice the local Sherwood number. Okay. So we'll conclude with this example. And then, okay, so it says 1 meter square thin plate of solid naphthalene is oriented parallel to a stream of air flowing at 30 meters per second. The air is 3104. The air is at 310 Kelvin, and then the pressure of the air is given. The plate is at 300 K. Determine the rate of sublimation from the plate. The diffusivity of naphthalene in air at 273 K and 1.013 times 10 to the 5 Pascal is given, and the vapor pressure of naphthalene at 300 K is given at 26 Pascals. So it says that determine the rate of sublimation from the plate. What do we need to do here? Once again, it is to know the flux and then multiply by the area. The area we are given, because it says the plate is 1 meter square. So we know the area. So what we have to do, the rate of sublimation can be found from this expression. So Kc delta Ca times A. You know, so everything about equation 1 is known except the mass transfer Kc. So this whole problem is about determining what the mass transfer is, and then the rest, the CAS and CA0 are given by the vapor pressure, and then the CA0, we assume that the naphthalene concentration in the bulk of the air is 0. So all we need to calculate then is the CAS from the vapor pressure. Okay. So to use equation 15, the Reynolds number and the Schmidt numbers must be known. Okay. So if you are going to use this equation, and we are not told that Schmidt number is equal to what? If we calculate the Schmidt number is equal to what, then it means that we have to go back and use the earlier one. Okay. So we have to calculate the Schmidt number, we have to calculate the Reynolds number, and then the diffusivity we are given, and okay, so the Reynolds number is given by this. The Schmidt number is given by this. Now, assuming ideality, the density of the air can be calculated as this. And then the viscosity is given. CA0 is equal to 0. That is, we assume the air does not contain any naphthalene coming in. That's when we say that Ca infinity is equal to 0. When Ca infinity is in a bulk, we assume that the air doesn't have any naphthalene coming in before it went over the plate. Okay. Now, CAS, that we calculate that is where PA is the partial pressure, the vapor pressure on the surface. Okay, well, I didn't get the numerical value, but the point is that everything you need is given. Okay, the Kc with these values you can get the Kc. The rho is here. The viscosity, I look for it, so I've given you a value for viscosity, so you can calculate everything. Okay. So I told you that there are various ways of getting the mass transfer coefficient. One was the dimensional analysis. Two, the exact boundary layer solution, which we just saw using the Blasius method that he used for fluid flow, applying the Blasius method to mass transfer and also to heat transfer. Then the third is approximate boundary layer analysis. The last one is the analogies between momentum, heat, and mass transfer, which we'll consider next time. Now, the approximate boundary layer analysis involves making material balance over a control volume in the boundary layer. This approach is useful in situations where exact solutions are unknown. So, when you can solve the complete, differential equation, and even the one that we saw, we have to make all kinds of assumptions and all of that. But okay, so in this case, you cut a certain this prism-like looking material of thickness delta x, but going in, we say that it is unit depth, okay, and we do a mass balance or material balance over this control volume, okay. So the volume designated by the block of length delta x, height del c. This c should speaking, be a subscript. And it's the thickness of the boundary layer. Delta c is the thickness of the boundary layer. And then that material that we are looking at has unit depth. And so if you are going to do a material balance on this, you have 3 ins. 1, 2, 3, 4. 3 ins and 1 out. Okay? So a steady state molar balance over the control volume gives W1 plus W3 plus W4 is equal to W2. So where WA is the molar rate of mass transfer of component A. The individual balances are given by, now the flux is given by CA times Vx, okay? And so you look at it this way. So you're looking at this, but it actually has mentioned in this. Okay, kind of. And so if you stand here, if you stand at this point and you are looking, mind you, you are looking at an area. You are looking at an area that is y in this direction, delta y. And then, so you are looking at a plate that looks like this. So you have to multiply this by this. This is your dy, but there is a width that is like this. So the fluid is coming like that. Okay. Is it clear to you? It's clear. Oh, okay. And then, if you look on the other side here, it's also like that, except that maybe this time is bigger. So the area, once again, since you are doing it again, it's a dy times a w, but the w is always unity. And so, if you multiply Ca delta Vx times dy times 1, if you like. Okay. And because the y is varying, so you integrate it. And this is what you get for WA1. So here, standing here. When you go here, it's the same thing, except that you are standing at x plus delta x. Okay? That's the WA2 going out. Now, WA3, that is not, you are not standing here or you are not standing. You are moving along delta x. Okay? And so what you do is you consider the quantity, this same quantity, flux, how it varies along x. Okay? And that quantity you multiply by the length, which is x. But the concentration at here, which we assume is up here, the same up here, it's just that we drew it in here. It is the velocity at the boundary, at the edge of the boundary. And so you multiply by Ca infinity. Now, WA4, that's nothing but the flux from the solid surface into the fluid on the surface. So you multiply by the mass transfer coefficient, and then the change in concentration. So the concentration at the surface, and then the concentration in the bulk. Multiply by the area, okay, which will be delta x times the unit depth once again. Okay, so if you need some further listing on it, you can ask. But later on, if you take your time and look at it. So here, in equation 18, all we've done is substitute all those terms into equation 17. Okay? And then we end up with this. Now, these terms contain the velocity profile, contain the concentration profile. So velocity and concentration profiles must be known to solve the above equation. These are normally not known and have to be assumed. In the previous situation, we took the continuity equation as our, if you remember, in place of the velocity profile. In this case, we don't know. So, excuse me. So a power series is assumed for the velocity and concentration. So these are the expressions that we want to use for the concentration variation and then the velocity variation. Okay. Now you notice that for the concentration Ca minus Cas, but here it's not Vx minus Vax, because that will be 0. Okay. Now these boundary conditions are conditions that must be satisfied. Vs is equal to 0, velocities are 0 on the surface at y equals 0. For concentration, is Ca minus Cas, because Ca is not 0. Then at the edge of the boundary layer, this is what you have for velocity, this is what you have for concentration. And then at the gradient at the boundary itself is this, because if for velocity, when you reach here, see, then the profile is steep, okay? It's not, it doesn't vary. From here to the edge of the boundary, you know how this thing is very small. But once you get to the edge, then the velocity is the same going, so it doesn't vary. So the second derivative are also 0. Now, if you solve, the concentration profile is given by equation 19, then the velocity profile is given by equation 20. Now, equation 19 and 20 are used in equation 18 here. Okay? And if you do that, somebody's done it for us, we end up with this expression. So this is what we obtain for approximate solution. Okay? It's the same, it's similar to the rigorous analytical solution. The only difference is in the coefficient. That one was, I think, 332? Yeah, 332 and 0.36. And so we say that the approximation solution is not bad after all. It gives you a good solution. But remember that what we've done is for laminar flow, steady state, and all. For turbulent flow over a flat plate with velocity, and for turbulent flow, one thing that would be different would be the concentration profiles. The concentration profiles will be different. Okay, the fluid is going to mix up more vigorously, and the concentration profile is given by this equation. The velocity profile is given by this equation. The concentration profile by this equation. And if you go to the mass, the Sherwood number for turbulent flow layer may be found to be this. Okay, so if you are solving a problem and it says that the flow is turbulent, how do you determine that the flow is turbulent? Maybe they'll tell you, or you have to calculate the Reynolds number, and then the magnitude of the Reynolds number will tell you whether the flow is turbulent. Or then you use this. Okay, so this will bring us to the end of, I think this is 7, lecture 6. Okay, yeah. 6, 7, and 8 are not too big. Those ones we can finish them next time we meet to finish them. Then we'll finish. Then after that, I will give you take home I. I'll give you take home I, and then after the take home I will give you the final exam. I think they've given a timetable for that. Yeah. So the take home I think you can take maybe 1 week, or I don't know if you need more. Don't mind. Then I'm thinking that the IA will constitute 60 or 70%. And then I'll give you a final exam. That one, you have to return it in 24 hours. That one, huh? 0 days. 2 days. Okay. So you return that one in 2 days.